Hi there, Mr. Sutton here with the BC Calculus 8.3 Part 2 homework solutions on vectors. On this problem, position of a particle is given by these parametric equations, x and y of t. We want the speed of the particle at time 2.3. So to get the speed, we're just going to do the square root of x and y prime of 2.3, both of those squared and added together. So basically this setup, x prime of 2.3 squared plus y prime of 2.3 squared. Just Pythagorizing that. Let's just go ahead and do that on the calculator. Now the nice thing is we don't actually need to know the derivative of x or y in order to do this, because we can plug in just a number to a function's derivative just using our calculator. So let's see how this works. So I'm here in my y equals. I've entered x as y1, and my y function I've entered as y2. Next, I'm going to quit out to the main screen. We've got, let's see here, square root, and I need the derivative of x at 2.3. So math 8, derivative, let's see, we'll do x, and then let me do alpha trace and get y1, that's my x of t, and then we want that at time 2.3. Great. We also need to go ahead and arrow over and square this because we're squaring x prime of 2.3. And then let me just do the same thing for the next thing. So we've got, let's see, math 8, derivative dx, alpha trace y2, and 2.3 again. Go ahead and square that. Press enter and hope for the best. About 3.413, which gives us choice C. On this problem, we have a particle moving along the curve y equals ln of x with an exponent whose velocity is given by this x prime function here. And let's see, we know the particle is at the point 1, 0 at time 0. At time 1, we want to know where the particle is. So this is basically a parametric vector kind of problem. We're going to start by getting the location, the x location at time 1. And then, since we know that y just equals the ln of x, we'll be able to use that to figure out the y location as well and get a full point out of it. Okay, so we've got, if we want to figure out x of 1, we need to take our initial x value, which is 1, and add to that the integral from, let's see here, we're going from time 0 to time 1, so integral from 0 to 1 of, well, what's the x function going to, what's the x prime function going to be? This function right here, t plus 1. Normally I would just write x prime of t dt in here. I'm going to write t plus 1 dt though, because this is a no calculator problem, so I might as well write this in here because I'm going to need to do this by hand anyway. So taking some antiderivatives, we've got, let's see, t is going to become 1/2 t squared. We still have that 1 out there, by the way. So we have 1/2 t squared plus this 1 is turning into a t, evaluating this from 0 to 1 now. So that's 1 plus all this stuff with 1 plugged in minus all this stuff with 0 plugged in. And we're going to have to simplify this mess to get an answer choice. So we can ignore this stuff with 0 over here. It just gets zeroed out. So we have, let's see, 1 plus, this is 1/2, so that's 3/2, plus another one is 5/2, so 5/2 when the dust settles. Now that's the x value. That is enough to pick answer choice C. But if you wanted to carry it out here, we've got y equals ln of x. That means y of 1 is just going to be the value of ln of whatever the x value at 1 was. So this. We're just figuring out the x value at time 1 and plugging it into ln. Well, here's the x value at time 1. It's 5/2. So y of 1 is really just ln of 5/2, which gives us the point 5/2 comma ln of 5/2. So that is definitively choice C. For this problem, we have a velocity vector given by a dx over dt and a dy over dt. And they're telling us at time 4 our position is 2, 1 for this particle. We want the y-coordinate at time 3. So this is basically an FTC with only one of these components here. We want the y value, so we're going to be using dy over dt. So we have our initial y value, which we said was 1. So, and we're figuring out basically y of 3 now. So y of 3 we can say equals 1 plus we need the integral from the time period here. So we're going from time 4 to time 3. So integral from 4 to 3 of the derivative of y. So we're taking the total change in y here. That's going to be, we'll just call that y prime of t dt. And now this is just plug it in the calculator. So in my y equals, I've just entered the dy over dt because that's all I need for this problem. The dx over dt we could enter, but it's completely irrelevant to this problem. Let's quit back to the main screen. So my setup here, I'm going to do 1 plus math 9 integral from 4 to 3. y1, I got that by doing alpha trace. y1, that's where I stored my y prime. Put a dx in there just because. And that comes out to about 0.590, which matches answer choice B. For this problem, we have the position of a particle given by these parametric equations. We want the speed of the particle at time 0. So we're just going to use our speed formula where we're taking the square root of x prime squared plus y prime squared at a specific value. So we've got the square root of x prime of 0 squared plus y prime of 0 squared. And if this were a free response, I wouldn't actually need to tell you what x prime and y prime were algebraically. I could just calculate those derivatives at a single point on my calculator. Most of the work here does take place on the calculator. Let's see what I did here. So I started in my y equals by entering my x of t and y of t functions. And I'm going to quit to the main screen now and do basically all of this. So this took a little while for me to enter off camera, but let me show you what I did. I did math 8 to get my derivative, dx, because we always do things in terms of x on the calculator. And x prime, I stored that as y1, so I did alpha trace y1 to get that. Evaluate that at x equals 0, and then you have to remember to stick a little square after all of that stuff. And then I did pretty much the same thing for y prime, where I stored that as y2. Again, I've got x equals 0, I've got squaring going on, so press enter on all of this stuff, and if you've done it correctly, it should come out to 16.209. So that's going to be choice D. For this calculator-based free response problem, we have a planetary rover traveling on a flat surface. Path over the interval from 0 to 2 hours is shown in this rectangular coordinate system up here. It's kind of going all over the place. And we're told that it starts at 6, 5 at time 0, and these are the x prime and y prime for its motion, based off some x and y that they're not going to define. Okay, so we want to find, for the first part here, the acceleration vector at time 1, and also the speed at time 1. So two things for the price of one on this problem. To find acceleration at time 1, well, we already have x prime and y prime, which is the components of the velocity. So acceleration is just going to be the derivative of these. So we need the x double prime and the y double prime at 1 hour. And because we're just taking the derivative of these functions at a single point, we don't actually have to tell anybody what those derivatives look like. We just have to plug it in our calculator, which I will do now. So the very first thing I'm going to do is I'm actually going to plug this x prime and y prime in as y1 and y2 on the calculator, because I've got a feeling I'm going to be using them multiple times in this problem. All right, let's quit out to the main screen now. So on the main screen here, I'm going to take the derivative of x prime at 1. So let me do math 8. There's derivative. We've got x. I'm going to do alpha trace y1. That's where I stored x prime. And I want to do that at x equals 1, giving me a value of about 19.975. And then let's go back and do the same thing for y prime. So I'm just going to arrow up here and steal my input from before, because I'm plugging in pretty much the same thing, only instead of y1, I'm going to do alpha trace and do y2. So let me arrow down to that, enter, and then let me just press enter, because that's where I stored y prime, was in y2. So that's negative 4.546. So there's our acceleration. Now we also need the speed. Speed is going to be the square root of x prime of 1 squared plus y prime of 1 squared. So basically Pythagorizing the components of the velocity here. So this setup here, oh, and we need miles squared per hour because that's acceleration. Or meters, is it miles or meters? Looks like it's going to be meters. Meters squared per hour. All right, on to speed. So we've got x prime of 1 squared, y prime of 1 squared, square rooting all that after we add them. So back to the calculator we go. And I've already got x prime and y prime entered in the calculator as y1 and y2. So let me just do square root then. Let me just erase all this. Square root. And let me do alpha trace y1. And I'm plugging 1 into that. So this is x prime of 1. And I need to remember to square that. Plus alpha trace y2. Plug 1 into that. Square that. Enter. About 11.678. And since that's speed, that's going to be in units of meters per second, or meters per hour, actually. For this next part, we want the total distance the rover travels over the interval from 0 to 1. So I basically need to take the integral of speed from 0 to 1. So I'll start with an integral from 0 to 1. And I'm going to be doing speed in here, so square root of x prime of t squared plus y prime of t squared dt. So all this stuff in here. And I definitely need to do that on the calculator. I don't have to write anything else out in here because, again, they defined x prime and y prime for me. So here's what all of this looks like on the calculator. Integral 0 to 1, square root of, and here's x prime squared, y prime squared. I don't need any parentheses with anything plugged in because I'm just doing the general function with a t as the input variable. All right, enter. And this gives us a total distance of, it's thinking very hard about this. Don't stop believing. Wait for it. There we go, 6.704. And what units is this? Well, total distance, that's going to be in units of meters. On this part of the problem, they want the y-coordinate of position for the rover at time 1. So I need to use my fundamental theorem on this y prime here. I have an initial y value of 5 at time 0. So I can say y of 1 is going to equal 5. That was y of 0, 5. Plus the integral from 0 to 1 of y prime. So this is going to add up all the little changes and give me 5 plus the total change in y. And now we use the calculator. So on the calculator, remember I've got y prime stored as my y2, so just 5 plus the integral of that from 0 to 1. And that comes out to 4.057 in units of meters because this is a position distance kind of problem. For this last part of the problem, the rover receives a signal at each point where the line tangent to its path has a slope of 1/2. Why does it receive such a signal? Who knows? But we want to know at what times between 0 and 2 the rover gets a signal. Okay, so we need to talk about the slope of this path here. Since this is defined parametrically, to do that, we need to say dy over dx equals y prime over x prime of t. So this is our parametric slope kind of formula here. And then we need to figure out when this has a value of 1/2. So here's the good news. We already have y prime defined as well as x prime. We've now defined the derivative and set it equal to 1/2. We can actually just plug this into the calculator now and see where this function intersects the function y equals 1/2. So let's go ahead and do that. So to actually do this on the calculator, so I don't have to do all this writing here, I'm going to go and define a third function, y3. And for that, I'm going to need fancy fraction here. I need y prime over x prime, so that's going to be y2 over y1. So alpha trace and y2. On the bottom, we've got alpha trace y1. There we go. But I don't want to graph all of these. Let me deselect y2 and y1 so I'm not graphing 3 things at once. And I only want to graph this on the interval from 0 to 2. So let me go to Window. And I've already got 0, I guess. But now I need 2 for my upper bound. Let me do zoom 0, zoom fit. Actually, hold on a sec. Before I do that, I also need to graph the function y equals 1/2. So let's see here. Fancy fraction, 1 over 2. There we go. All right, now let me go to zoom fit, zoom 0, and we'll see where those intersect. So here is the first one. Well, that's kind of crazy looking. Okay. That's really gross looking. And the line y equals 1/2, I don't see that anywhere. So what's happening here is we have this vertical asymptote at x equals 0 apparently. And this is a big issue. It's kind of dragging this whole window down. So what I'm going to do instead is I'm going to just manually make my window something a little nicer. I mean, look at this, y min negative like almost 400. Let me do y max 5 is fine. Let me do for a y min, let me do like, I don't know, -3, whatever. And let's try graphing this. Okay, that's a little more reasonable. So this is where you have to sometimes take what the calculator gives you and insert human judgment to get what you need. And there's my line y equals 1/2 going through. It looks like it only touches in one spot right here. This is more asymptotic if you zoom in. So let me do second, and let's see, second trace, intersect, option 5. And let's do enter, enter, enter. There's our intersection point at 1.072. So that's going to be in, let's see, hours, and that's the time of intersection. On this problem, we have a particle going along a curve with these parametric vectors here, and at time 2, our particle's at 1, 5 for the position. We're also given dx over dt and dy over dt. And on these problems in general, based on the number of things you have to do, it's always great if you start with the velocity components here. So for our first part is the horizontal movement of the particle, left or right at time 2. And explain your answer. And then another one, find the slope of the path at time 2. So read carefully because there's two different things we needed to do on part A. Let's start with the horizontal movement. Horizontal movement, we're talking about dx over dt, and whether that is positive or negative. That'll determine whether we're going right or left. So to figure this out, I just need to plug 2, the time that they're talking about right here, into dx over dt. Let me do that on the calculator. So the very first thing I'm going to do before I do anything else here, I'm going to enter dx over dt in my calculator as y1 and dy over dt as y2. So here's what that looks like. And I used my fancy fraction form for y1, dx over dt. I know I'm going to use these multiple times, so it's good to have them in there. All right, now I just have to quit out to the main screen. And I just needed to do y1 of 2. I just need to plug 2 into dx over dt. So alpha trace, and then y1 of 2. That's going to come out to about 0.271. Significantly, that is a positive number. That means that in terms of left-right motion, we must be going to the right at time 2. All right, so that was the first part of part A. For part 2 of part A, they wanted the slope of the path of our particle at time 2. So for that, we're essentially talking about dy over dx. That's what slope really is. It's a delta y over delta x. dy over dx evaluated at 2. For this, you need to use your derivative of a parametric equation here. This is going to be y prime of 2 over x prime of 2. And we just need to plug those into the calculator now. So here's what this looks like on the calculator. Y prime, which I stored in y2, I'm doing that upstairs. Downstairs, I've got x prime of 2, y1 of 2. Enter, and that's about 3.055. So there we have it. For part B here, we want the x-coordinate of our particle's position at time 4. Since I have the derivative of the x value here, I just need to use my fundamental theorem. I've got an initial position, so we always do initial position plus the integral of the derivative over the time interval. So I can say x of 4 equals my initial x value of 1, plus I need an integral of, let's see here, we started at time 2, we're going to time 4, so integral from 2 to 4 of x prime of t dt. That's all I have to show for my setup. And now the rest of it is just entering this in the calculator. So here's what this looks like on the calculator. I have 1 plus math 9 integral from 2 to 4. Now remember, I stored x prime as y1 already, so I don't have to rewrite all that. Dx, press enter. and that's about 1.253. On this next part, I want the speed and the acceleration of my particle at time 4. Well, for speed, we're doing the square root of x prime of 4 squared plus y prime of 4 squared. Basically, taking the x and y components for velocity, squaring them and adding them together, Pythagorizing them. I'm going to do this all in the calculator. So here's the setup on my calculator. I've got the square root of, and I stored x prime as y1, so I've got y1 of 4, and we're squaring that. And I stored y prime as y2, so we're plugging in 4 and squaring that as well. Press enter, and that's about 0.575. We'll take their word for it. Next, I need the acceleration vector at time 4. So basically, I need x double prime of 4 and y double prime of 4, whatever that comes out to. We're going to calculate that on the calculator. Now, here's the good news. Since I'm only calculating the derivative of x and y prime at a specific point, namely 4, I don't actually need to tell you what x double prime looks like algebraically, or y double prime. I can just calculate those derivatives completely on the calculator. So let's do that. So for x double prime of 4, I'm taking x prime, which is y1. I'm doing math 8 to take the derivative of that, dx here, and x equals 4, and pressing enter to get about 0.041, and that's negative. So that's the first part of our component for our acceleration. Going back to the calculator now to get the other piece of this, to get the y double prime of 4, I can actually just yank my input from before up here, press enter. But now instead of doing y1, I'm going to do y2 in here. So alpha trace and then arrow down to get y2, because that's where I stored y prime. So this is really doing y double prime now at 4. And enter for that, about 0.989. So there's our acceleration vector. For this last part, I want the distance traveled by my particle between times 2 and 4. So for this one, we're basically going to take the integral of the speed on the interval from 2 to 4. So I have an integral from 2 to 4 of, and now basically what I wrote for speed, we've got square root of x prime of t squared plus y prime of t squared, all of that with a dt. And I already have x and y prime entered on my calculator, so let me just go ahead and run those numbers. So here's what this looks like on the calculator. Math 9, integral 2 to 4, square root of, and this is x prime squared plus y prime squared. Use a dx, whatever. And then that comes out to, survey says, about 0.651.